Okay, Organic Chemistry 2342. Here's continuation of Chapter 18, Part 3. We're going to continue on some reactions in these alpha carbons of carbonyl compounds, okay? So now we're going to look at some nucleophilic reactions we can use with these materials by alkylating the alpha carbon next to the ketone, okay? So the first thing we want to do is we want to use a strong base like LDA to give us an irreversible deprotonation to give us our product here. And what it's going to do is LDA is going to give us it's going to deprotonate our site that is least sterically hindered. And so it's going to give us our kinetic product, okay? So when we do this, we are able to form our nucleophile enolate base here. It then acts as a nucleophile to displace bromide to create a new carbon-carbon bond. Okay, so let's use that in additional reactions right here. Sorry. So in this case here, we're going to start with our our ester here, and we're going to deprotonate at this position here using LDA to give us our nucleophile. And once we form our nucleophile, we can then displace iodine from this alkyl halide to generate our product here as our methyl ethyl butanate. Okay, so we still have our ester intact, and all we've done is added alkylation at that alpha carbon. Okay, we can do this same type of reaction using the cyanide group as our electron withdrawing group to deprotonate from this alpha carbon here. And once we deprotonate once, we can get this to act as the nucleophile to displace iodine and give us our branched nitrile compounds. Okay. So we also have an opportunity to make enolates out of the beta dicarbonyl compounds. What this means is that when we have a single ketone, like in this group here, we only have this alpha proton here, and the pKa is between 18 and 20, okay? By adding a second carbonyl group, we get an additional electron withdrawing in both directions here, meaning the acidity of this hydrogen increases. And so we can actually use weaker bases like alkoxide to generate those enolate ions, okay? So once we can have this more acidic proton here, we can generate our negative charge, and then this acts as a nucleophile that we can use in various reactions. So let's see how we can use that. One way to use that is to have a carboxylic acid right here, and that we have a ketone on one side. So this would be a intermediate we could form using this. The interesting thing about having this beta dicarbonyl compound, if we have this acidic hydroxide on the carboxylic acid, what can happen is we can get a catalyzed decarbonylation to happen. So we will end up with our terminal methyl ketone. Or in the case of if we have this functionalized group here, we can again decarbonylate it, ending up with our ketone. The way this happens is that because there's a proton here on the carboxylic acid, it can actually rearrange to form this six-membered hydrogen bonded ring. Once we form that six-membered hydrogen bonded ring, it transfers the hydrogen to the ketone right here, and that allows us to have electrons kick in and the electrons kick over here. So we end up generating CO2, and we end up generating our enol. Once we formed our enol, it of course can tautomerize to go back and forth between the enol and the ketone. Okay, so the key step here is you must have one, an acidic proton, and two, it must be a beta dicarbonyl so you can form this six-membered ring, okay? So how can we use this in synthesis? Well, one way we can use this in synthesis is we can use what we call the Malonic Ester, okay? A Malonic Ester would be to take this compound right here, which would be the malonic acid right here, and we convert it into the carboxylic acid ester so that we can then create our nucleophile out of it. Note, we have to use it as the ester. If we had protons on there, the base would just remove those protons and the reaction would progress no further. So we typically use it as the ester formation, so we have no acidic protons, or so that this is our most acidic proton. In addition, typically we use an ester that has the same group as the alkoxide we're forming, because what can happen is the alkoxide can come and displace this. And so if you had a combination of methyl and ethyl, you would end up with a combination during the reaction. And so what we typically do is to have, if it's a diethyl compound, we're going to use the ethoxide as our nucleophile. So, I'm sorry, as our base. So once we have our base in there, we deprotonate at this position in between the two carbonyls, our alpha position. That creates our nucleophile. Our nucleophile can then do a nucleophilic substitution on our alkyl halide. And then in the last step here, this is the acid catalyzed decarbonylation. Okay, so when we do this, we hydrolyze off these, then we generate the six-membered hydrogen bonded ring, and we remove one of the carboxylic acid groups, leaving the other carboxylic acid group there. Okay, so this is a great thing for creating any alkyl halide to turn it into a carboxylic acid with a total of 2 carbons added to it. So if, for example, if you had a hexane here, you would end up with octanoic acid. Now, this is different than the reaction we learned in the last chapter, where we can take a Grignard reagent and react with CO2 to create a carboxylic acid. That adds 1 carbon chain to the chain. This reaction does 2 carbons to the end of the chain. All right, so how does it work? Well, of course, the first step is we start with our ester here, and then we use the alkoxide that is the same as the ester we have. It gives us a deprotonation in between the 2 carbonyl groups, which turns it into a nucleophile. Once we get that nucleophile, we end up with our neutral substituent here. And then with hydrolysis, we end up getting to the dicarboxylic acid compound, which can then now form that protonated 6-membered ring to decarbonylate and give us our carboxylic acid. Okay, so what's really interesting about that, besides just adding the 2 carbons there, is that if you control the reaction correctly, you can get a monosubstituted reaction and a disubstituted reaction. So you can get a very complex carboxylic acid if you need one. So the simplest reaction is to take your diethyl ester and react it with the ethyl alkoxide right here, then use it as a nucleophile, and then during this step right here, we're actually saponifying and clipping off those esters to give us carboxylic acid. The second step, we're actually doing the decarbonylation. And what's going to happen is one side's going to be clipped off, giving us this hexanoic acid from our butane right here. Okay, so that's great for monosubstitution, but if we want to disubstitute it, the first step is exactly the same. We generate our alkoxide right here. We generate our nucleophile, and we get our first substitution on it. But before we go to the hydrolysis step, we actually have to use a stronger non-nucleophilic base to get to form the second anion. And once we form that second anion, it can still act as a nucleophile and generate our disubstituted alpha carbon. And once we get our disubstituted alpha carbon, the first step, of course, is going to be hydrolysis of the ester to give us the carboxylic acid, the dicarboxylic acid. Then the intermediate in the decarbonylation, of course, is that 6-membered ring, and followed by the remaining product is our dialkyl carboxylic acid. Okay, so if we want to do one, we can use a weaker base like alkoxide. If we want to do 2 substitutions, we can actually do them symmetrically or unsymmetrically, because we do it stepwise, first with that alkoxide and then with the T-butoxide for the second step. Okay, and that completes this section.